Thank you so much. Thank you for giving me this opportunity to present. Like you said, my name is Ivo or Ivelin, and this is some work I've been doing on a study of the kinetic Sunyaev-Zel'dovich effect, particularly the patchy component and the 21 centimeter power spectrum, combining them to better understand the properties of the epoch of reionization. And this is work that I have done also with Ivelin Georgiev and Harold Melema, who is in the public. So, I guess I have to click by hand. So there's really no purpose to describe the epoch of reionization in this meeting. There's a lot of expertise, but I also wanted to put my favorite image here anyway, because it seems kind of fun. I just wanted to point out that something I find quite cool is that much as we've discussed about the IGM perspective, the 21 centimeter power spectrum is giving us the view of the neutral IGM, and the power spectrum at different redshifts is giving us information within that period of time. Now, even though there's a lot of expertise, I'll talk about this a little bit more. And I said this before to superimpose this, if this works in English, the phrasing, with another probe of the epoch of reionization, particularly the patchy kinetic Sunyaev-Zel'dovich effect, which comes about from the scattering of CMB photons with free electrons associated with ionized bubbles during the epoch of reionization. They inverse Compton scatter, and you can imagine as the bubbles are growing, this effect is gaining more and more of credence. It becomes more pronounced. And it's an integrated probe that conveys information of the ionized medium, but also about the properties of reionization in a different capacity. And what's very interesting about this is that already there's some very curious work, you can see here, where there's some constraints claimed of the amplitude for one of the angular scales of the PKZ effect. And you can see a model of the PKZ. It has a very distinct and interesting shape. And in that one, there's information about the epoch of reionization. So particularly the authors give constraints on the duration of reionization, but it's worth pointing out that the morphology is also encoded there in a different way. And of course, even these detections are model dependent. So this is just to drive the point that a joint study of both of these will help us infer the properties better, but also help verify our inferences of the 21 centimeter power spectrum. But what have I been doing? So I'm actually presenting this work and aspects of this work, which is a published paper. But of course, I have a limited amount of time, so it's just certain parts. But it all sort of boils down to this analytic expression, where to the left we have the 21 centimeter power spectrum, and to the right we have a whole bunch of terms, most interestingly the one in solid, which is the autocorrelation of the free electron density field, and it is an essential component for constructing the PKZ. And what's interesting in this expression, again, is a sort of bridge between the two. And we want to know then if we generate one or the other, then we can compare them, or we can generate both probes simultaneously, as we do in our inference, as you'll see later on, and then use that information to better constrain the properties of reionization. But of course, you will note that there's other terms around. There's the density field, the power spectrum, which we know quite well from the CMB, the ionization history, of course, and these sort of interesting terms that capture some sort of cross-correlation between the density field and the ionization field, or even more bizarre, such as the product of the density fluctuation in the ionization field and the density field. I will refer to these as high-order terms sometimes, but maybe I should really be saying cross-correlations or complicated cross-correlations. But I presented you now with some equation, but I just want to give you credence that these two terms are actually related to each other. Here you see the power spectrum of the 21 centimeter signal with the hydrodynamic simulation R-SAGE at a fixed K scale, and it's evolving with redshift. You see some of the distinctive shapes of the 21 centimeter power spectrum. And the full expression matches this perfectly. And of course, this is true for our SAGE, but also for other simulations I've checked with C2Ray and 21 centimeter fast. But maybe that's no surprise. What would be more interesting would be to sort of get rid of these cross-correlation terms and see if we can recover the same feature and not worry about them in the first place. What we find in this work is that it's not really so simple. I can't really remove one or the other and get the same feature. In fact, you see a biasing. Let's say the midpoint of reionization, this very characteristic peak, is sort of shifted. Let's say the power spectrum drops down much earlier, indicating an earlier end of reionization. But what's more crucial is also the k-scale. If I were to show you these two terms and how removing them from here varies across different k-scales, it's not self-consistent. It changes with different k and it changes with z, because these cross correlations are quite complex and you can't really remove one without the other. You need a very good understanding of both to create them into a model. But what we did find in this work is that sticking to the simplest form, the one in blue, where the higher order terms, both of these are removed, you get a sort of shape that follows the main features of the power spectrum, but is biased in a sort of self-similar manner, one that we hope to sort of either marginalize over or include as a free parameter that we can study, because there is interesting information there. And much of the work afterwards is done on a forecast of the blue, taking this as true, a forecast exactly extracting reionization parameters. But of course, we have actually compared how far off we are from the true power spectrum as well. Yes, just to show you in a different type of way, this is now the dimensionless power spectrum, and the true, of course, is the one generated from the simulation. And now the fuchsia is actually our model, here seen in blue. You can see that it matches pretty well in the regions of interest between 0.1 and perhaps not 1, but 1, 2, around here, which is a sort of sweet spot for many radio telescopes such as SK, Hera, LOFAR, MWA, choose and pick. So how do we actually construct this? Because we're going to make this we're going to make an inference of this and use an MCMC. Well, to generate the 21 centimeter power spectrum, we need the density field, and this we get from CAMP. We generate ionization histories using the asymmetric fit used in the Planck analysis. And we actually use a parameterization of the electron density autocorrelation based on this work by Girish et al. 2020, where they fitted this to the RSH simulations. And this all sort of comes down to having 4 parameters that we study: the mid and the end point of reionization. These are quite obvious, but maybe alpha naught you can understand as an amplitude parameter, a contribution of the power spectrum of the electron density field, and kappa, which is a sort of cutoff scale that gives you information. In this case, in this capacity, it gives you information about the average bubble size throughout reionization. Anyway, now that you have this, I just wanted to put a picture like this from the paper, where each row has each of these 4 parameters: the midpoint, the endpoint, the amplitude parameter, and the cutoff, and they're varied across our prior ranges. And you have the ionization history against redshift, the power spectrum of the PKZ. And for the sake of this work, though we study different redshifts, of course, we have chosen these 2 redshifts to present. So what you can get from this is you can see how when you vary the midpoint or endpoint, you get different global histories, of course. Maybe you're impacting, there's less of an impact on the redshift dependence of the power spectrum here on this, but you impact the PKZ in one type of way. Well, for example, here when varying kappa, there's less effect on the mid and the end point, but it affects, there's a k-scale dependency introduced in how the power spectrum behaves. This is just to show you that some of the parameters, for example, follow, some are degenerate in each other in some way, while the others in another. But essentially, we're looking for the complementary parts where we can discern them. Now, because we've built this forecast, I should also mention we assign noise. We assign thermal noise based on the specification of the telescope and assume some integration time. And we include sample variance, or cosmic variance, you could call it. But for the PKZ, we just add an uncertainty based on the current observation. And we have a lot of freedom to choose the number of data points we have. But for this work, we chose a sort of early SKA design, where the hope is that we would observe maybe 1 or 2 K scales at some redshift. In this example, we've chosen a lower redshift because the thermal noise is lower and 1,000 hours with SKA, but we've also looked at 100 hours. And the goal is to show you here in this slide how the joint analysis of the PKZ and the 21 centimeter signal is complementary. You can see the parameter space is quite well confined in blue, but because this is a joint analysis, I can turn one data set off and run the analysis or the other. So for example, in fuchsia, again, is the same analysis, but then just with the PKZ data point. So it constrains the parameter space in one way, it's biased, maybe it's sensitive to the duration of reionization, but not to the started endpoint. The opposite is true for the 21 centimeter signal. Perhaps it's quite sensitive to when reionization has ended or its duration, and together we can constrain this in this parameter space. And then we play around in the paper using different noise estimates. For example, because each telescope has a unique setup, of course, we can look at what would happen if we detect an observation with LOFAR or MWA or the SKA. How well will we be capable of constraining our parameter space given the setup of this telescope? And of course, these are different redshifts actually and different K scales. How in the work we look at how different K scales will help us constrain one type of information, not the other. But it opens the opportunity for conversation and further tests, such as if we had 2 observations from 2 telescopes, could we combine them together in this framework to better understand our parameters? I talked a lot about just having 2 observables, but you can see here that 2 observables, 2 P21 data points, but in this case, they are 3 and the K is a data point. So going just from 2 to 3, we managed to get very, very, very good constraints on our parameter space compared to the initial priors. And this shows that the parameterization is working quite well. Actually, it's much smoother than before because it's not having convergent issues, but you can even see now some of the degeneracies are becoming more pronounced. But this is interesting because it offers potential for future work. 3 data points will definitely not be enough in the true case, and it will be very nice to try to create a more complicated model for the noise, add a residual foreground or different types of varying noise, and really try to change and see how many data points one needs in those cases to start constraining reionization in the first place. Well, I was meant to put a timer for myself, but I can't see. But I think I should probably speed it along in any case. Sorry.
A minute, maybe.
Oh, I have a minute. Then it's good. Sorry. The way that the forecast is working is that we actually can include, we calculate tau, the Thomson optical depth. So there's also the natural opportunity to either use the Thomson optical depth as a prior or actually sample it from the from our analysis and then make a P21, PKZ, and Thomson optical depth joint analysis. Okay, well, if it was a minute before, it's probably 30 seconds or less now. So I'll put my summary and conclusions. I hope I've shown you that there is a natural benefit to studying the PKZ and P21 together, and doing a joint analysis will help us understand the properties of reionization, of course. But maybe more interesting for this conference, it will also give us a way to verify our inferences on the 21 centimeter. Okay, but thank you so much. I cannot really see you. So
thanks, Ivelin. So we can take a couple of questions.
Was I okay on time? Okay. Oops. Sorry. Go back.
Or you can write it in the Slack also.
Yeah, it's no worry.
Yeah, you can also pick up questions from Slack if somebody is.
Who is checking? You can.
I'm checking. So, and Ivo is there in the Slack, so he can.
Yeah, I can see. Don't worry.
So
Right now, there is none.
There is none, okay. Okay, if there is no question, then thank our speaker, Ivelin.
Thank you.